Mechanical characterization of stir-cast Al356-B4C composite. Abstract: the development of lightweight material for industrial utilities attracted aluminum composites, as this material have superior mechanical properties over unreinforced alloy. The present investigation focused on utilization of boron carbide into Al356 alloy fabricated by stir casting. The boron carbide particle weight fractions of 3, 6,9, 12% weight of particle sizes 53 to 106 m were reinforced into matrix material. The scanning electron microscopy, SEM, was done to see distribution of the B4C particles in the matrix. The evaluation of mechanical properties, viz., tensile strength, compressive strength, density, and hardness were carried out. It was found that the tensile strength, compressive strength, and hardness of the metal matrix composite, MMC, increases as weight fractions of the B4C particles increases. Also, density of composite decreases subsequently. So boron carbide has potential to fabricate strengthened metal matrix composite for diverse alloy applications. Keywords: MMC, stir casting, B4C, Al356, SEM, hardness. Introduction. Metal matrix composites, MMCs, are the combination of metal matrix and reinforcement or filler material which gives excellent mechanical properties, and they are classified according to reinforcement type or its content. MMCs have ability to achieve any combination of stiffness, strength, and density. The principal matrix materials for MMCs are aluminium and its alloys. The major advantage of aluminium matrix composites over other materials such as steel are increased specific strength and stiffness, lower thermal coefficient of expansion, wear resistance, lower density, and good corrosion resistance. Metal matrix composites, MMCs, have received substantial attention due to their excellent strength, stiffness, lighter and wear resistance for tribological, aerospace and marine industries. Though MMCs possess superior properties, they have not been widely applied due to the complexity of fabrication. The conventional stir casting is convenient processing method for fabrication, as it is relatively inexpensive and offers wide selection of materials and processing conditions. 1. Stir casting offers better matrix particle bonding due to stirring action of particles into molten aluminum. Among various reinforced used, boron carbide particulate reinforced aluminium composites possess a unique combination of high specific strength, high elastic modulus, good wear resistance and good thermal stability than the corresponding non-reinforced matrix alloy system. Hence, composites with boron carbide as reinforcement are possible to overcome the cost barrier and wait for widespread applications in bulletproof Ts and armor tank. Manufacturing of aluminium composite by stir casting is one of the most economical methods of processing MMC. In this project, silicon carbide and boron carbide particulate reinforced aluminum alloy matrix composites are produced by stir casting process by varying the particulate addition by weight fraction of Al, 90%, SiC, 5%, 6.5%, 8%, and B4C, 5%, 3.5%, 2%. Microstructural changes of the cast composites are studied by using metallurgical microscope and scanning electron microscope, SEM. 1. The paper is the result of investigations made on microstructure and mechanical behavior of 3 and 6 weight percentage of nano-sized B4C particulate reinforced to Al7075 alloy composites. Al7075 matrix composite having nano-boron carbide was fabricated by liquid stir casting method 2. Metal matrix composites, MMCs, have been widely investigated and used in automobile and aerospace industries due to their advantages of improved strength, stiffness, and increased wear resistance over the monolithic alloys. Also, considering limited reports on the study of weight percent influence on wear characteristics of Al6061 boron carbide, B4CP, composites. This study presents the effect of weight percent of B4CP in Al6061 alloy matrix on wear loss during dry sliding wear in pin-on disc tribometer at different wear parameters against oil-hardened non-shrinking, OHNS, steel disc at room temperature. The composites are prepared by stir casting technique. Tribological investigations were examined according to the L9 orthogonal array of Taguchi. The influence of percent of reinforcement along with load, speed, and distance were examined for the wear loss of composites. 3. Boron carbide is one of the potential neutron shielding materials, and its use can be maximized for structural shielding application by dispersing it into metal matrices such as aluminum. Dispersion of B4C and its interfacial stability is a major issue during its processing. This investigation is on the synthesis of B4C reinforced 6061 aluminum matrix composite by liquid, metal stir casting technique under optimized conditions after solving the issues related to the processing and evaluation of the structural, mechanical, and interfacial characteristics. During processing of composites, pretreatment of B4C particles is necessary to improve its dispersion for aluminium matrix composites, AMCs, reinforced with nano-sized MgO particles are widely used for high-performance applications such as automotive, military, aerospace and electricity industries because of their improved physical and mechanical properties. In this research, magnesium oxide, MgO, nanoparticles were synthesized by solution combustion synthesis process. The nanoparticles were characterized by powder X-ray diffraction, PXRD. A 356.1 aluminum alloy was reinforced with 0.5, 1.0, 1.5, and 2.0 Wt% of the synthesized magnesium oxide nanoparticle, via stir casting technique. 5. 2. Experimentation. A specimen preparation. B4C reinforced aluminum alloy, Al356, composites, processed by stir casting route was used in this work. The three types of stir cast composites had a reinforcement particle size of 53 to 106 m each. The required quantities of boron carbide, 3, 6, 9, and 12 Wt%, were taken in powder containers. Then the boron carbide was heated to 4500 C and maintained at that temperature for about 20 minutes. Then weighed quantity of Al356 alloy was melted in a crucible at 8000 C, which is more than 1000 C above liquidus temperature of the matrix alloy. The molten metal was stirred for 10 minutes to create a vortex, and the weighed quantity of preheated boron carbide particles were slowly added to the molten alloy. A small amount of Mg, 1 weight%, was added to ensure good wettability of boron carbide particles with molten metal. After mixing, the composite melt was poured into mold for the preparation of specimen. Table 1 shows the chemical composition of the Al356, Table 2 shows its mechanical properties, and Table 3 shows the major chemical composition of the boron carbide. B. Mechanical testing of composites. Microstructural analysis done by XRD and SEM with standard metallographic process to check uniform distribution of reinforcement of B4C into aluminium. The tensile tests were conducted on MMC samples according to BS 1490 at room temperature, using a universal testing machine. The specimens used were of diameter 13 mm and gauge length 62 mm, machined from the cast composites with the gauge length of the specimen parallel to the longitudinal axis of the castings. The wear tests were conducted as per ASTM G99 using pin-on-disc setup. The specimens used were of diameter 10 mm, and length 100 mm machined from cast composites. The Brunel hardness tests were conducted in accordance with the ASTM E10. Density measured as per BSN 1706:1998/BS 1490:1988 in laboratory. 3. Result and discussion. A. Microstructure analysis. As the microstructure plays an important role in the overall performance of a composite and the physical properties depend on the microstructure, reinforcement particle size, shape, and distribution in the matrix alloy. Prepared samples were examined using a scanning electron microscope, SEM, to study the distribution pattern of boron carbide in the matrix. Fig. 5. Microscopic views of 12% boron carbide reinforced in Al356 at 100x. The microstructure of MMCs clearly shows a uniform distribution of boron carbide in the matrix, Fig. 2, 3, 4, and 5, with no void and discontinuities observed. There was good interfacial bonding between the boron carbide particles and matrix material. However, in few composites the particle clustering occurred in some places, and also some places were identified without boron carbide inclusion. During fabrication, the particles were added into the molten alloys was observed to be floating on the surface. B. Density. Density values of the boron carbide composites decreases linearly with addition of boron carbide particles. The decrease in density of composites can be endorsed to lower density of boron carbide particles, 1.9 g/cc, than that of the unreinforced Al alloy, 2.76 g/cc. The level of density increases with boron carbide Wt% as shown in Fig. 6. 20.79 95.84 64.17 36.64 36.190501001001501234 density in kg/cm3. The tensile strength increased with an increase in the weight percentage of boron carbide. Therefore the boron carbide particles act as barriers to the dislocations when taking up the load applied. Good bonding of smaller size boron carbide particles with the matrix is the reason for this behavior. The tensile strength improves from 154.27 to 186.65 MPa, which is almost 20% improvement. The decrease in the tensile strength of the samples with boron carbide weight fraction beyond 5% is due to the poor wettability of the reinforcement with the matrix and due to clustering of the reinforcement particles. The composite D wear strength. Samples are prepared with L/D ratio as 10.0, so length of specimen is 100 mm and diameter is 10 mm and 6 mm. Further samples are polished to achieve flat surfaces with emery paper. Wear test determines load applied 20 N and 250 rpm of time limit 10 minutes. Observe the initial weight of pin sample before use of test. For wear test for removing material and final weight observe shown in Fig 7. Wear strength increases with increasing percentage of boron carbide particulates. However, the wear strength of the composites begins to drop when the boron carbide content increased. Beyond 9 Wt%, the boron carbide particles interact with each other of compared to base metal matrix composite. Hardness. Samples are tested as per STD BSN 1706:1998/BS 1490:1988. For Brunel hardness test, surface being tested generally requires metallographic surface finish. And it was done with help of 100, 220, 400, 600 and 1000 grid size emery papers. Fig 9 variation of BHN with Wt fraction of boron carbide. The results of the hardness test, Fig 9, show increase in hardness with the weight fraction of boron carbide. It shows that hardness increases by almost 11% in 16% boron carbide composite as compared with alloy. 4 conclusions. 1. Addition of boron carbide increases mechanical properties of composites. 2. Hardness of composite increases with increase in boron carbide percentage. 3. Tensile properties of Al-B4C composite increases with increase in boron carbide. 4. The mechanical properties viz., tensile, hardness etc. increase due to hard boron carbide particle. 5. Wear resistance of Al-B4C composite increases due to presence of hard boron carbide particle. 6. Due to stirring, grain refinement helps to increase mechanical properties. 7. From microstructure study, uniform dispersion of B4C particle enhances mechanical strength of composites.